Dear ladies and gentlemen, the following presentation is with subtitles. You can recognize this by the symbol CC in the control bar here of the video. Please click on the symbol CC, then the available languages of the translation will be displayed. Please note that the translations were produced by machines and therefore no guarantee can be given for a correct translation. Dear ladies and gentlemen, dear colleagues, the title of my presentation is the Digital Calibration Certificate, the DCC. My name is Siegfried Hackel and I will give this presentation. The basic presentation is intended to highlight the basic principles of the DCC. There are some jump points in the presentations, some of which refer to other presentations. There will also be more in-depth discussions with the presentation. They are represented by a small comic man running behind a DCC with a butterfly jet and trying to catch it. When you see this symbol, it refers to an excursion where a certain part of the presentation is explained. These slides are framed in blue to make it easier to see them in the slide bar. And the slide bar is here under. So you have the possibility to either inform yourself briefly about the DCC or to go deeper into detail. The digitization in metrology refers to a lot of fields. In this lecture, the focus is the digitization in the field of calibration. Here you see as an example the calibration pyramid for Germany. On the top there is the NMI of Germany, the PTB. And the PTB carries out about 5,500 calibrations per year and passes on the corresponding measurements and weights primarily to accredited calibration labs. These in turn pass on the weights and measures to the industry until the product is finally released. This multiplies the number of calibrations. For example, there are calibration labs that perform as many calibrations in one day as a PTB performs in 1 year. Here you can also see the integration of the legal metrology with the calibration as an example here for this. The overall metrological system must guarantee that the data balance is still accurate enough so that there are no problems with the calibrated balance at the postal company. Such calibration pyramids exist overall in the world, and ring comparisons are used to ensure that each NMI is then able to pass on its measurements and weights in such a way that the same measurements are taken everywhere. It should also be pointed out that the measurement uncertainties play a very important role. In general, the NMIs have a much lower measurement uncertainty than the laboratories below in the calculation pyramid. The first foundation refers to norms and standards. They are valid for the DCC as well as for the analog calibration certificate. The digital SI is the basis of the DCC. There are other things that are important for calibration, such as GUM. They are also taken into account into the DCC. The output report is implemented as specified in the ISO 17025. The second foundation is a hierarchical structure within the DCC. Let us look for the administrative data. The administrative data reflects the first page of the analog calibration certificate. Here, for example, it is noted what was calibrated or who performed the calibration or when the calibration was performed. These and other things are in this area. It is strictly regulated. This also includes the results of calibration as far as it is possible to regulate it. For the DCC, we specify that the SI unit system shall be used by applying the DSI. The primary representation shall always be SI to avoid confusions within machine-to-machine communications. Unfortunately, these confusions are not rare. There were already very large damages because of such confusions. For this reason, we have attached great importance in the observance of SI units. The design of the DCC cannot be regulated down to the at last details. If you look how calibration certificates from the most diverse areas appear, that becomes immediately clear. For example, a calibration certificate from the field of acoustics looks completely different from the field of cyclotron radiation. The DCC guaranteed the flexibility. Here it is necessary to raise the threshold for the joint presentation of results for the same applications. We call this good practice applications. The development of good practice applications will be an essential task for the future. I would be very much welcome if one of the results of this meeting could be an arrangement to create good practice applications. The third ring here is the area where unregulated comments can be stored, which are only marginally have something to do with calibration. Therefore, we have called it this area comments. Ring 3 can, for example, contain information about the billing for the calibration service. One could store the invoice for the calibration here. The fourth ring is intended for human-readable parts of the DCC. This area can have a very individual character. Besides the SE units, other units can be displayed here. As an example, the blood pressure in medicine, which is measured in millimeters of mercury instead of Pascal. Let's move to the third foundation. The third foundation is XML. XML as exchange format is proven itself internationally. The standard has been in use for about 20 years. It is well established and is very often used. XML is already suited when dealing with documents. Furthermore, data from XML can be transmitted into other exchange formats like JSON or MQTT. There are important applications to attach cryptographic signatures to XML documents for security purposes. In this way, it's achieved that the content cannot be changed. If all these three foundations are cleverly combined, the DCC is obtained. Let us now move to the comparison between the DCC and its analog counterpart. First of all, it is important to note that the DCC includes a human-readable version. There are many advantages of the DCC in comparison to the analog certificates. The obvious advantage is that there are no media breaks anymore. In most calibration labs, the measurement results and the results in the measurements itself are performed with IT assistance. This raises the question whether it makes sense that the data and results already available in IT systems are printed out on paper. Of course, it is an advantage during transport because there are no postage costs and, in addition, the DCC can be used in several places at the same time. In the factory itself, the transfer from the paper to the IT system no longer needs to take place. There, and that's what really happened, the data is very often re-entered by the 4i principle. The second point is that all data is available in a clearly defined form. A global standard can clearly regulate which information is at what position and what the information is called. This massively reduces the error rate. The third point is that the DCC fully complies with existing norms and standards, such as RAMI 4.0. There also applies for Industry 4.0 or IIoT. Here, integration can be realized without major effort. Safety and security aspects are also considered in the design of DCC. The long-term availability of the data is given, and the information is stored with integrity and authenticity, which is realized through the use of digital signatures. International standards were also added here, which have their origin in the PDB. In the metrology community, we are in the position to implement very rapid standards worldwide. Due to the legal task of the NMIs, we can quickly set standards here. And these standards are in demand by users in industry. We do not have the time to push forward standardizations via, for example, ISO, because this process takes far too long. Our core competition is in demand here, and if we set a DCC standard, the world would follow us. Sweet. An ISO standard can be made at any time afterwards. Let us come to the last point on this slide. The use of DCC is economically efficient. Because the changeover from the analog to the digital process means a low migration effort. The return of invest is very favorable, which means that the company gets back their invested resources very quickly. A much higher process efficiency is achieved by its conversion to digital processes. Above all, there is a high increase in quality, which goes hand in hand with the introduction of DCC. Now we have arrived at a point where I would like to offer you an excursion. Within the framework of the EU-founded Ampere project called SmartCom, it was determined what the general requirements for the DCC are. If you want to participate in this discussion, please click on the link above. Now I would like to show the classic workflow of a calibration. The calibration of a cyber gauge service as an example. Canterpillar gauge is well suited because it is widely used. The calibration is done by means of gauge blocks, the photo. The calibration starts with a collection of the administrative data. Then the measured data is collected and analyzed. A wide variety of methods and solutions have been developed here. It must be clearly pointed out that many supported procedures are used for calibration. Handwritten analysis should practically no longer occur. The procedure for the digital calibration certificate does not differ so far from the procedure for the analog calibration certificate. A new aspect of the DCC is that the results is no longer printed on paper. Instead, the data is transferred to the XML file here. This process is compatible to filling out a document template to generate an analog calibration certificate. How does the transfer of the calibration data into the XML file take place? At the beginning of the presentation, I've shown you the hierarchical structure of the calibration certificate. In the first 3 levels, here shown, in the first 3 levels, purely machine-readable comments are shown. The third level for the comments can be filled individually, for example, with the invoice of the calibration. The first 2 levels must now be filled with the calibration data. They are filled from the administrative data as well as from the measurement and resulting analysis. Of course, the import of this data should be automated. Therefore, it is necessary to use a lab-specific middleware, here shown. Because, as already mentioned before, calibrations are very individual and cover the entire fields of physics. The middleware ensures that the results are placed at the intended location in the XML document. It's shown here. There will be a whole presentation session on the topic of middleware. As an example, I would like to refer to a lecture whose link you can see here. Here you can see a typical example of a middleware. It is based on an already installed IT environment. It is remarkable how quickly the middleware can create it in this example. The accuracy of information on the calibration certificate is checked by a human being. Since the results so far are available in XML, the next step is to convert these results into a human-readable format, as shown here. XML can be, in principle, read by humans, but it takes some time to get familiar with it. Furthermore, the digital calibration certificate should be a human and machine readable. First, a post-processor, which is shown here, is required in conjunction to a layout middleware, generates a view as required by the German accreditation body, for example. I assume that the web-based representation in HTML5 will become generally accepted in future. Then you will also have more flexibility, for example, in the presentation of large tables, because you are independent of the usual paper format such as A4 or letter. The resulting human-readable document can then be checked. Here for this procedure, you will see another presentation, and here is the link. The resulting human-readable document can be checked. If the document is incorrect, the process starts again at an earlier point. If the result is correct, the human-readable version can be transformed to XML. The transfer is based on the base 64 standard. With base 64 routines, which are implemented in very many tools, all available file formats can be converted to XML and vice versa. After this step, all information is contained in the XML container, as you see it here. Consistently, it is maintained as the human-readable document is created from the machine-readable parts of the DCC. Let us now look for the interaction between the XML schema file and the XML file. The XML file contains the documentation itself, stored in elements and attributes. The XML schema file, on the other hand, defines the elements as well as the attributes that determine the structure of an XML data record. Of great importance is the possibility is a property of validating the XML data record against an XML schema. The combination of both, here shown, the combination of the XML schema and the associated XML file ensures that the properties defined in the XML schema are mapped in the XML file. In the case of DCC, This is a conformity with ISO EEC 70025 and the possibility of transforming the XML file into other formats, such as JSON or MQTT. In this way, an Industry 4.0 compatibility is achieved. This is why the structure of the DCC XML schema is so important. Validation ensures that the structure of all DCC XML files is the same. Let us now look at the structure of the DCC XML schema, shown here. In the upper left quadrant, the hierarchical structure you are familiar with is shown. In the other three quadrants, the structure of the corresponding XML schema file is displayed using different software tools. The two software tools below are available for free. Because the software tool shown in the upper right quadrant provides, in my opinion, the best graphical representation, I will use this software tool in the further courses of the lecture. Let us now turn to the ISO IEC 70025 and its implementations in the DCC schema. Different levels of mandatory and optional informations are necessary to meet the requirements of the ISO IEC 70025 and the long-term availability of data. We distinguish between 5 different conditions. For example, the element containing the unique number of the calibration certificate is mandatory. The name of the element is unique identifier. Mandatory regarding to the long-term availability of data is, for example, the documentation of software used to generate the XML files. This element name here is DCC software. Partially mandatory is, for example, the date when the calibration material was received by the calibration laboratory. ISO EEC 70025 requires a specification of this data in case that the specification of this date is relevant for the calibration. This information can be useful if the calibration material changes over time. Hopefully, this should not be the case when determining the mass of weights. Therefore, in case, this information can be omitted. The element name is receipt date. Then there are optional fields, but these become mandatory due to other circumstances. An example is a calibration laboratory code required by the German accreditation body. The element name is Calibration Laboratory Code. Finally, there are optional elements. One example is the software used for calibration. It can be specified, but generally does not have to be specified. The element name is used software. Let us now look at the DCC XML scheme in detail. Here we see the hierarchical structure of the DCC in a new form. The root element is called Digital Calibration Certificate. Let us now turn our attention to the area of the administrative data. The following elements are mandatory. The element DCC software. Because long-term availability of data is required, it is mandatory to list the software used in the creation of the DCC. This refers only to the software with which the XML files were generated. Element country code ISO 3166_1. Of course, it is important to know in which country the calibration laboratory has carried out the calibration. This is important in order to identify the legal area. The country is indicated according to the ISO 3166 Part 1. Element used language code ISO 369_1. It is also important to know the chosen languages of the DCC. The country is specified according to the ISO 639 Part 1. Element mandatory language code ISO 639_1. It is then also important to indicate which of the languages should be used in case of doubt. Element unique identifier. The use of a unique calibration certificate number, for example, the unique identification of the DCC, is also mandatory. It must be specified before the element is signed. The hash value is unsuitable as a unique calibration certificate number because a person cannot extract any additional information from these large hash values. The date of signing of the DCC is not listed in the DCC itself. It is specified as part of the signing process. Let us look now for a DCC excursion. At this conference, I would like to make a proposal on the structure of the unique identifier element. This proposal can be found in the DCC excursion. Interested participants, please follow the corresponding link. Let us now turn to the other mandatory fields in the field of administrative data. The element begin performance date and end performance date. The ISO IEC 70025 requires the indication of the start and the end of the calibration. Very often, an identical date will be entered here. Let us now turn to elements that contain a whole family of child elements. The reason for this is that the information is much more complex than it could be stored in only one element. Element items. The identification of the calibration items or item also belongs to the field of the administrative data. Element calibration laboratory. The name of the calibration laboratory and its address is also mandatory. Element responding persons. The same applies to the responsible persons. Typically, the name of the person in charge of the calibration laboratory is listed here. At least one name must be given. Element customer. Of course, the customer is also a mandatory field. I will give you a deeper view into the administrative data in the following excursion. Here I will go into the structure in more detail and show how, for example, optional fields can be handled. In particular, I will deal with the elements with child elements. I will also deal with interactions with entering data in an exemplary way. For example, more than one responsible person can be named. In this case, one person with overall responsibility must be named. Here is the link for the excursion. Let us now look for the area of the results of calibration. In the case of mandatory elements, it depends on whether the specification applies globally to the entire calibration process or not. Because there may also be areas where the specification are only valid for one measured value. This is also the case in the element used methods. That's the reason why I display here global and local. In many times it will be the case that the used method of calibration is valid for the whole calibration process. In this case, this method must be specified in the range that applies in the entire DCC. However, there are also quite a few cases where the method used changes during the calibration process. In this case, the specification of the method used must be linked to each individual measured value, since a global statement is no longer possible. What applies in the element used method applies exactly in the same way in the element influence conditions. Of course, the result of calibration must be stated in a calibration certificate. The element for this is called results. At this point, I would like to refer to another DCC excursion. In this excursion, the area measurement results will be discussed in more detail. It is very important that the SI units are used in this whole range of measurement results. Here I like to read the presentation of Daniel Hutchenreuter, who talked about the importance of the SI for digitization. Here you can find the link to this lecture. I would like to emphasize once again the importance of the SI data format being ideally suited for machine-to-machine communication. It is universally defined and unique. Only the use of clearly defined SI units avoids misunderstandings. This leads to enormous costs and can even be a danger for life and health. Now we consider the meaning of the non-SI units. Of course, non-SI units also have the right to exist, providing they are clearly defined. I do not see medical doctors moving away from measuring blood pressure in millimeters of mercury over the next decade. Confusing millimeters of mercury and hectopascal is even dangerous because the conversion factor is about 3 to 4. A mix-up can be harmful to life in this case. It has been shown that SI units are now used in many areas, although nobody would have thought this possible in the past. One example is air pressure. In many countries, the air pressure is now given in hectopascal. So it would have been difficult to imagine 50 years ago. How can I integrate non-SI units for the human-readable output of the DCC? What is required? There are two things: the definition of the non-SI unit, name and symbol, and a reference that defines the non-SI unit based on SI units. I will give you two examples that are of importance for the economy. The unit psi, which means pound force per square inch, and the unit Grad Oechsle for the density of sugar in the wine juice, a parameter which, as I said, plays a major role in German economy. The slide shows how the unit Oechsle is defined in the statements section of administrative data. First, you give here a statement that you do a definition, which is valid in Germany. Here is the reference norm, where you see in which part of this norm it is done. And then Here you give the name, Grad Oechsle, and here you give the unit. Then everything is defined. How is a non-SI unit applied to human readable part? This is done via the element SI hybrid. In this element, the value is first entered as the unit in the SI system. In the following step, the value of the non-SI unit are then entered. When the measured values are output in the human readable area, the value is then output in SI units as well as in non-SI units. The procedure guarantees that the conversion from the SI system of units to another system of units is done in the calibration laboratory, in other words, by specialists in units. This serves to reduce errors. Let's go back to the slide that shows the essential elements of the DCC. The human readable information stored in the document section has often been discussed and are subject of my presentation. Throughout in the conference, several presentations will also deal with it. Therefore, I will not go into this topic in detail here. Let us now turn to the missing element comments. This element is intended for the inclusion of information that are not directly related to the calibration in the sense of the ISO IEC 70025. In the context of my presentation, I had pointed out that it is the case. For example, the calibration laboratory could send the invoice of the calibration. The scope of application can provide much more for the whole user community of the DCC. The customer of a calibration product have often remarked that it would be an advantage to better connect the calibration order with the overall process of calibration. Therefore, additional orders are often placed with the calibration laboratory that do not directly belong to the calibration process itself. Here is a reference to another DCC excursion. Here I discuss the idea of a digital calibration request, DCR, and a digital calibration answer, DCA. Many elements from the DCC can be found in the DCR and DCA. Also, other metrology certificates show these similarities. This results to the following approach. Applying the metrological semantics of DCC to other areas of metrology and economics around the DCC. I expect that after this DCC conference, the metrological semantics of the DCC will be further considered, and that on this basis, a reliable foundation point for DCR, DCA, and other applications can be created. Please look to this DCC excursion if you like. Let us now turn to the area of securing the DCC against manipulations and the traceability of who the DCC exhibitor is. In the case of digital data, this is only possible by cryptographic technologies. Electronic signatures are used in many countries about the world. In Germany, for example, there have been electronic documents of high importance secured by electronic signatures for well over 10 years. Examples of this are the Civil Status Act, the Waste Management or government producement. Here too, XML data are secured by electronic signatures. In Europe as a whole, it was agreed some time ago that electronic signatures from country A should also be recognized in country B. This is regulated by the eIDAS directive. It would be very interesting for me to find out on how the handling of the digital signatures is regulated in non-European countries. Do similar agreements exist there? Please give me some information on this. Slido is welcome. The Europe-wide validity of electronic signatures means that, for example, that an electronic document signed in Switzerland in accordance with the regulation is also recognized in Sweden and vice versa. This is a major advantage because it allows the cross-border of using DCCs in Europe. But now, what does the world look like? Here we have the problem that the regulation has not yet been extended to all countries of the world. This is a limitation for the universal applicability of the DCC and many other things in the field of digitization. It is therefore essential to consider how to solve the problem. On this slide, I have outlined two approaches to solving the problem. On the one hand, one could use the excellent cooperation of the national metrology institutes to build up a regulation similar to the eIDAS directive for metrology in the world. Mutual trust exists among the NMIs, and it is repeatedly demonstrated, for example, in ring comparisons. The idea is that the metrology community agrees to trust each other also for digital signatures. Another possibility would be to establish a trust anchor for the cryptographic infrastructure for metrology. The trust anchor could then be the CIPM or the CIPM Bureau. The similarity with the structure we already know from the excursion to the unique identifier here becomes clear again here. I refer to this excursion here as well. The technical effort required to operate a trust anchor for cryptographic signatures should not be underestimated. There are possibilities to have such a trust anchor operated by IT professionals. This is a common business model. During the excursion to the universal requirements for the use of the DCC, to whose link I would like to refer again here, various requirements were formulated. One requirement was that it must be possible to cancel a DCC. This means that it must be possible to retract a DCC. Here the question immediately arises how this should work in with a non-haptic item. After all, an electronic document, once issued, can be copied as often as desired. Therefore, returning it to the exhibitor does not work. The withdrawal of electronically signed document is not provided for the eIDAS directive. Although the problem has been addressed to the working group, implementation is not yet in sight. Furthermore, a political agreement is necessary for this. In principle, there is already a solution for the problem because if I lose the signature card, there are mechanisms to block it. The keyword is OCSP request. The Same mechanisms could also be used to control the withdrawal of the electronic signed documents. We cannot wait until there is a Europe-wide or worldwide solution to this problem. Therefore, even in analogy to the already existing solution, the OCSP request, a database could be set up in which the hash values of the valid DCC are stored. If a DCC is withdrawn, this is noted in the database. A comparison with this database then allows the withdrawn DCC to be recognized immediately. I would like to talk about the industrial benefits of the DCC. Let us take a look at the basic structure of a factory. First, we look at the part of the machine where we want to call a supplier part. The planning of the component, the design, the virtualization, the commissioning, the production, and the utilization and optimization is shown here in terms of the time. The first 3 to 4 steps belong to the area of modeling, and the rest belongs to the area of the reality. The time representation of the machine consisting of several components looks similar. And the model can even be extended to the construction of a whole manufacturing plant. The red arrows show the links between the machine parts, the machine, and the factory. Why do I show this? Because calibration plays a role. Let us first look for the previous analog calibration certificate as they are used here. The calibration certificate of the part of the machine plays a role in commissioning and production. Because at this point, at the last, I need to know how the machine part behaves. And during production, I need the calibration certificate to document my quality standards. The same applies to the set of calibration certificates at the machine. By analogy, this also applies to the entire factory. What does the use of the DCC charge? A lot. Because the DCC can already provide valuable information during the planning phase. Its strength is partially evident in visualization, because the DCC can already be seen as a digital twin which describes the measuring accuracy of the part of the machine very precisely. On the next slide, I will report further on the digital twin. What applies to the machine part naturally also applies to the machine. By the interaction of the DCC, the individual components can also be visualized better. And what is valid from the transition from part of the machine to the machine is also valid for the combination of the several machines into one factory. This is exactly one of the advantages of Industry 4.0 in combination with the DCC. The German Ministry of Economy and Energy Lighthouse project GEMIMEC 2, which was launched a few months ago, will address this aspect. At this point, I would like to refer to the presentation of the speakers of the project. Let us now move to a project where the presentation just shown will be implemented. The implementation will take place in the framework of the GEMIMEC 2 project at the Wind Energy Competence Center at PTB. Here is an illustration of the wind turbine on which torque transducers of hitherto unknown size are to be calibrated. To compare the size of the plant, a person here is shown next to a torque transducer for the wind turbine. This huge machine will be completely digitized as part of the Lighthouse project. Here a schematic representation of the Digital Competence Center Wind Energy DCC is shown. At the bottom of the left, a calibration order is shown. The aim is to create a digital calibration certificate for the torque transducer, here see at the bottom right. A modular fragmentation of the plant is to be represented by the puzzle species. In addition to the ambient conditions here, which significantly affect the measurement, the calibrated good itself, shown here in yellow, is equipped with many sensors, shown here. In the whole area of the facility, many more sensors are installed in order to be able to record the measured variables necessary for the calibration. All these components are interconnected with the help of a control system here. The measurement is controlled on the one hand. On the other hand, the simulation of the entire processes takes place here. The measurement results of all the sensors are collected and stored in a database. And the respective measured values then interact with the respective known DCC of the individual sensors via a computer simulation, shown here. In this way, the object being measured is calibrated and a digital twin of the entire system is generated based on the overall results. This data can then be uploaded to the cloud as it is protected against manipulation by cryptographic means. It is also possible to store the data in the cloud in encrypted form so that only those who are authorized can access the data. What else can you do with digital calibration certificates? It is essential that, due to the greatly expanded possibilities offered by digitization, we are also able to use the complete result of the calibration. I would like to illustrate this with an example. Once again, my example using a caliper gauge is used. In the graphic, first 4 measurement points can be seen, and they are necessary for the calibration. If one would increase the calibration and take up considerably more measurement points, one would be able to determine measurement values shown in the following diagram. It is immediately visible that this caliber gauge measured exactly between 3 and 8 centimeters distance. This knowledge could be used to the benefit of the industrial applications. But also, the use of the DCC as a digital twin is immediately obvious here. It would be quite imaginable, for example, that the display of the caliper gauge could be provided with the correction function here that is delivered from the measurement graph. Thus, by the using of digitization, a cantilever gauge can get much higher accuracy than it had before calibration. Another example is the calibration of air pressure sensors. It is known that air pressure sensors have a certain drift in time, here shown. In this representation of results from several calibrations, a trend is present. This allows an estimation in the future, which can be quite important. These two shown examples open completely new possibilities in the field of calibration. These can also lead to changes in the regulations for standards for calibration in certain areas. For example, it is conceivable that recalibrations, which were regulated in previous standards by specific intervals, may be replaced by other regulations. Now I would like to take this opportunity to point out another DCC excursion. Here the production cycle is explained in more detail. It is about the interaction between calibration and the use of calibration material in industry. An excursion to the calibration process within an industrial company will also be discussed. You may now have thought how you can get access to all the things I presented to you during the presentation. We would like to grant you this access as the DCC is a project for the meteorological community. We are happy to share all the information with you. The DCC scheme is freely available on our website. Here you can see the first parts of a line of a DCC. The source for the XML schema of the DCC is already stored here. A much more elegant option is our developer platform GitLab. Some of you already have access to this platform. If you want to have access to this system, please write a personal note in Slido. This development platform contains a lot of information besides the DCC scheme itself. A description of the individual elements of the DCC is also available here. It is not yet finished, but it is being driven forward at a fast pace. Furthermore, you have the possibility to actually start new activities or comment on existing issues by entering questions. We would be pleased if you would actively participate here, as many have done before. Let us now turn to the outstanding issues where we have not yet been able to move forward. These points are also noted in the DCC scheme. That's a snapshot out of the DCC scheme. No feedback from the communities has been received so far. My hope is that the conference will enable us to work on the areas that are still open and achieve a consensus. Which areas are these? It is about material collections, the way external ones should be treated, and in which way the metrology traceability can possibly be further developed, and how to deal with different calibration locations. Close to the end of my presentation, I would like to point out two excursions. The first excursion concerns to the comparison between a standard that is partially applied in industry and the DCC. The second excursion, or the final excursion in this lecture, will focus on the national quality infrastructure. Here is the link. In this excursion, I will show how the national quality infrastructure of a country is built up. If you have a lot to do with calibration, please have a look at this excursion. This excursion shows the important role of the calibrations in the national quality infrastructure. I would now like to take the opportunity to thank the DCC team at PTB for their great cooperation and support. Without these colleagues, none of this would have been possible. I thank you for the attention you have given to my presentation. Please do not hesitate to use Slido to enter your presentations and comments here. I look forward to the DCC conference and the lively discussions with you. Bye.